Okay. Can you able to see my screen here?
Yes, sir.
Okay. Thank you. That's what the unit 3 design of analog IIR filters. The main content that is going to be covered in this chapter is characteristics of the practical selective frequencies, how I take a selection, how I make the frequency that is selection, and which are the commonly used the mathematical approximation methods. One is Butterworth approximation method and another one is Chebyshev type 1 approximation method, and design of analog FIR filters. So after understanding the Butterworth and the Chebyshev, then later on we try to design the analog filters for the same. And then frequency transformation. Frequency transformation is nothing but I have a lower frequencies, I want to design the high frequency, or I want to filter high frequency components. So design of I have a low pass filter. Can it possible to transfer to band pass filter? Can it possible to transfer to high pass filter? That is what we call it as a frequency transformations. Okay. Now, now before to that, what is a filter or why filter is required? Both in one point. Okay. To make sure to understand this particular, I have some figures and try to identify these, observe the operations that are performed by these machines. What is this machine called? Decorticator, groundnut decorticator machine, it is called as. What it does, so input for this system, no machine, I can replace with system, right? This is one of the system. What is the input for this system? So input for this system is a complete groundnut. A groundnut consisting of a complete which is having a wrapper plus the groundnuts, right? So I have both of this, right, within this, like this. Now, these are the input signal for this particular system. So now this I will call it as a system, and this is the input. What is the output from this? There are two parts. One is wastage and another one is groundnuts, right? Okay. So there are two components that are coming out from this system. Okay. Now one more figure. So this is called as the rice puller machine. The input for this system is a complete paddy batta. So where after the processing, I have the rice at one side and the chaffs at another side, right? So the chaffs at another side and rice at the one more side. Now the paddy consisting of both the rice plus chaff, right? Chaff. So now I'm this, if I call this as another way, I call this as a one signal. This signal consisting of two signals, I am trying to separate the signal 1 and signal 2. I am trying to separate signal 1 and signal 2 with a system, and the system name is rice miller, machine, right? Here also this consisting of two signals. This is signal 1 and this is signal 2. I am trying to separate them, where the initially a signal S1 and S2 are combined in a signal called S. Of when I enter into this system made sure that this is going to be separated, right? Now can I call these two systems as a filter? Can I call these two as a filters, right? So similarly, if the same concept is used, I have a system. I have a system where my signal is x of t. What do you mean by this x of t? This x of t signal consisting of many other signals. So that's, in other way I can call it as rise is one signal with some frequency f1 and another signal f2, right? So there are two important components that are present within the pad. Similarly, x of t is a one signal which comprises of maybe two signals, maybe three signals, maybe n number of signals, which means that when I say that different signals, it is nothing but it's consisting of a f1 frequency component, f2 frequency component, f3 frequency component, and it continues. I don't know how many frequency component combined to form a x of t. Now I want to analyze the individual frequency components, right? So f1 frequency I want to separate, f2 frequency components I want to separate, f3 frequency component I want to separate. Now what I should do, I need to have a one system, and that system I call it here it as h of t. Now, what is the operation that is going to be performed in regular in time domain? It was convolution that what we performed. This is what we performed, and that itself, the operation of convolution, behind convolution, what we are trying to do is we are trying to filter. We are trying to filter, and as I told you, this is in a time domain which is not possible to separate these frequencies f1, f2, f3, so on. What we do is we go for moving from time domain to frequency domain. That's it. When I move from time domain to frequency domain, what happens? The system I apply the system, and this system now not h of t, h of s, and this system is not x of t, x of s, and this system not y of t, y of s. That's it. Now what is to be designed? You know that output, right? In any system you take, okay, you take a the decorticator machine, you know what should be the output. ನಿಮ್ಗೆ ಔಟ್ಪುಟ್ ಏನು ಬರಬೇಕು ಅಂತ ಗೊತ್ತಿದೆ, ಇನ್ಪುಟ್ ಏನು ಇದೆ ಅಂತಲೂ ಗೊತ್ತಿದೆ, right? So you know that what is the input for this system and what is the output. Here also you know what should be the input for the system, what is the output for the system. Oh, I know what is input, I know what is output, I already know this. So that is what I need to design. What? X of y of s by x of s. That is what that I need to design the system. I need to design the system. Only if you know input and output, then only it is possible for me to design the system. This is practical implication. Many times what we do is we will be given a h of t value, and we will be given you a y of t value. We calculate a x of t. We ask you to calculate y of t, but it is on paper it is correct. On theoretically I teach this is how you are supposed to perform circular convolution. This is how you are supposed to perform the linear convolution as such. But is that the way to design practical things? Is it the way to interpret the practical things? No way. What is to be done? I should know what input I should give for my system, output I am trying to predict, output I am trying to predict. Then only it is possible to design such systems, right? So here also frequency, I have some frequency component. I know which all the frequency component are present in my system, and what is the input for that system. So I know input, I know the output. Now what is to be designed? Design a system. What type of system you need to design all the time? Yes, the system should be linear time invariant system. Why it is called as a linear time invariant? So if I switch on my laptop today and time invariant, today I am trying to switch it on by 8:30. Tomorrow if I switch it at 10:30 in the morning, it has to turn on. It is not a time variant. Time variadange adu change agbardu. So it has to be time invariant. ಏನರ time ಇರಲಿ, the system has to run as it is. That's what the meaning of linear time invariant system. So what is the condition? What are the conditions to meet these linear time invariant systems, LTI system conditions? One is bounded input, bounded output, and another one is stable and causal, right? Causal, right? So this is what the main import, and the system is memoryless, right? So do you mean to say that the system has to store how many kgs of decorticator, how many kgs of if I put these groundnuts today, 3 kg, should it remember tomorrow yesterday I put 3 kgs as such? No, it is not required. So system can be memoryless. No need to remember these how many kgs yesterday I put the groundnut into the decorticator as such. So that's where the concept of the linear time invariant systems lies. Okay, so another very important concept, that's this I think probably I covered in one of the class. See, now look at this. This is one white light which is a combination of 7 different colors, which is nothing but this one which is having a signal, okay, x of t, which is having a signal of some frequency f. I know that it is going to be split into f1 frequency, f2 frequency, f3 frequency, f4, f5, 6, 7, right? 7 different colors, which means that, what does it mean? It is nothing but 7 different frequencies. 7 different colors means 7 different frequencies, 7 different signals, right? Oh, similarly, if I need, I don't know, I forgot the frequencies. Just let me assume that f1 is a lower frequency and f7 is a highest frequency. Maybe I'd be wrong also. I have not encountered those. Now assume that out of which, out of 7 signals, uh, I need only first 3 signals, which are lower frequencies. What you do? What you do? I apply a filter which is low pass filter. So I apply this filter because I need, out of 7 frequency components, I need only lower frequency components, f1, f2, f3. So I go for applying the low pass filter. Okay, I want to have f7 to f5 to f7. So what it is now? Higher frequency. So I apply a filter. Now my signal is something like this, high pass filter. No, I want a middle frequencies. Let me take F3, F4 and F6. Now I want to have this middle frequencies. So these frequencies. So now this is what we call it as band pass filter. These from one band, that is from band 3 to band 5. So these signals I required. So what is this? So this is what band pass filter. This is what low pass filter. This is what the high pass filter. Right? So now I need to design my system accordingly. That's it. So this is what here Prism is called as a system. The prism is called as a system. And in mathematics, in mathematics, now this is exactly the same as, this signal is exactly the same as x of s, and these 7 frequencies exactly nothing but a y of s, and this prism is nothing but my system h of s. Now what is to be designed? Prism is to be designed, right? So which performs this operation, which splits into this signal. So that is what we go for. See, it is not possible in my time domain. I cannot pick individual frequencies. It is not possible to pick the individual frequencies that are present in my white light. So what I do, I move from time domain to frequency domain. Now, since the input signal is continuous based on, see, based on the signal is continuous or discrete, I apply a mathematics for this. If the signal is continuous, if the signal is continuous, then if you want to go for frequency analysis of that, then the mathematical transform that I use is Laplace transform. If the signal is discrete, and of course I should also make sure that whether the signal is periodic or aperiodic here, and if the it is aperiodic in nature, then obviously I should go for Fourier transform for this, right? So this is what one has to understand in designing any systems. Okay, so that's where if you go back to your network analysis, how the signal was continuous, right? The signal was continuous, right? Like this, and then you apply Laplace transform for these types of signals where V of s and output was y of s. So you try to design the such systems v of s, y of s by v of s, where v of s is a continuous time voltage, where input was x of t or vi of t, v out of t. So that's where you applied Laplace transform for such a sequence. Similarly, in case of control systems also, your input for any system that you are trying to design was the system where was designed with respect to signal, where the signal was continuous in nature. So hence there also we applied the Laplace transforms, right? So this is once again now what chapter we are discussing. We are discussing analog filter. So I am trying to design analog filter, and let me call this as IIR. Why IIR? Once again I'll discuss this later point of time. But the reason for Laplace is the signal is analogous. The signal is in nature of x of t. That's very important. That is one important point here, and this is one more important point: low pass filter, high pass filter, as such. Okay. I hope you got this particular concept here. Okay, moving further. Now you tell me what is the definition for filter. So it is nothing but in the signal processing. With respect to signal processing, the filter is nothing but a device, a process that we try to remove some unwanted components or features from a signal, right? So which are the unwanted components here? See, for my requirement, maybe if I consider f1, f2, f3, I feel that f4 to f7 are not required for the right now for the processing. That's what unwanted. Okay, not it doesn't mean that waste you are trying to remove it out, right? So in the as I told you, in the groundnut decorticator, so groundnut is also important for me, and the waste is also important for some other things. I'll put it for some domestic usage, right? So here also the same thing, probably f1, f2, F4, F5, F6, F7 is not required for me, but it doesn't mean that for other application also it is not required. For my application, maybe that particular frequency is not important, so important. I use a low pass filter and I take out only F1, F2, F3 components, right? So as such. So that's where we define a filter as a process or a device that remove unwanted components. Which is once again a class of filtering is a class of signal processing. Okay, where features of filters being complete or partial suppression, which is main important. We are trying to suppress the frequency components which are not required. Okay. Now, the another important study what we do moving further is practical frequency selective filters. We try to design the filters in such a way that based upon the characteristics of nature. I'll tell you what type of character it is, which is we call it as usually we talk about the order of the filter here, characteristics. When I say that, I'll talk about what is order of filter in a later case. Now, in order to design, design, so once again I need a the mathematical approximation methods, and these two are the mathematical approximation method. That is, one is Butterworth approximation method and Chebyshev type 1 approximation method. These two that we use in your syllabus to uh, design low pass filters or high pass filters. Okay. Now, this is Butterworth approximation method. Like, look at this. See, when I call it as I want to design a low pass filter, okay, which is nothing but in a frequency domain. When I say that frequency domain, I put is in a what is that? What type of graph? Semi-log graph, because everything we try to analyze in terms of decibels there. Okay. Now this is what a practical ideal filter. I talk about the ideal low pass response, right? So this is how from 0 to, from up to some cutoff frequencies, right? So in case of Prism, as I told you, from 0 to f3, right? Now the other thing is my voice signal is ranging from 0 to 20 kilohertz, right? Within this, let me assume I need only first half samples or lower frequency values, which means that from 0 to 10 kilohertz. Now this 10 kilohertz, I call this as a omega c, which is nothing but a cutoff frequencies, right? Only these signals I want to perform the that particular signal, which consisting of a different frequency levels of a signals, right? When I talk for half an hour, all the entire half an hour time, I my signal variation will be consisting of n number of frequencies within that, right? Ranging from 0 to 2 kilohertz, highest is 2 kilohertz. So in that perspective, if I want to analyze only the below 10 kilohertz frequencies, I take how many samples that exist here and I try to analyze. Similarly, this is what ideally speaking, this is how the uh, the waveform or the output should look like. Okay. Now, uh, but it is not possible for me. Approximately, we approximate my signal in this practically speaking. So we try to design our filter in this form. So that's what and with this particular point, we call it as a pass band attenuation, and this is called as a stop band attenuation. See, if my signal is something like this, a speech signal, okay, if I call this, I try to design one filter. So it has some higher peaks also, but I'm trying to attenuate, I'm trying to stop that. So that is where we call it as a I'm trying to pass those signal. That's where we call it as a pass band attenuation. And there are some signals which are not able to transform here, which are not able to transform. That is, we call it as a stop band attenuation. And here also, if I take some frequencies are passed and some frequency cannot be passed completely I'm speaking, because it is not to the ideal curve, right? It has to get, it should get me edge. See that there is a difference of this many frequencies. I'm losing these many frequency components here, right? So when I design the practical filter, so that is what we call it as a transition band here. If you observe carefully, this is what we call it as a transition band. What is this transition band? Which is nothing but a pass band and stop band frequencies. Pass band and stop band frequencies. These frequencies are completely allowed, and here onwards the frequencies are some frequencies are allowed and some frequencies are missing. So that's where the pass band frequencies we call it as. So this is the here onwards lower. That's what I told you here. So this is what we call it as attenuation of some signals. There is, I'm trying to stop because of my practical approach. Okay. Now, what is this figure talks about? this is how one ideal low pass filter should look like in pictorially. Now I need to design mathematical equations for this. Then only it is possible for me to come up the 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 filter like this, right? So how do you do it? I have parameters, these parameters what we discussed. Okay. Now, before moving to mathematical equation for this, let me give you some analogy how the mathematical equation is going to occur. Now, look at this. Can you able to give me? So, this is a signal where some x and y axis which consisting of some straight line, I call this mathematical equation as y equal to mx plus c, right? I have a figure. If I want to write a math equation for this, this is how I try to write. Similarly, I have a one more signal which is an exponentially growing signal, so I call this as y equal to e to the power of 80 as such, right? So now this is the math equation. This is the math equation for this figure. And there is one more figure which is called as a parabola, right? Somewhere else, this is x minus a whole square is equal to h minus k kind of thing, right? So this is my parabola equation, right? Some constant. So this is my parabola equations, right? So this is math equation for parabola. Similarly, now guess the mathematical equation for this figure. So we know that since from the childhood days we are very versatile with analyzing these mathematical equation and vice versa. If I have a mathematical equation, I can draw this figure, or if I have this figure, I can observe that, oh, this is how the figure varies, right? If I have this equation, this is how I try to plot it, right? So similarly, now what is the point is, I have this particular figure. Now what could be its equivalent mathematical equation? I need mathematical equation for this, right? So this mathematical equation, which is approximation. So this is what we call it as approximated value, right? Which is approximated, which is mathematical approximation equation was given by a first name called Butterworth, the name of the scientist. He gave the name, his name is kept for this equation, and hence it is called as a Butterworth approximation method. And one more person came and he made a slight alteration because there are some disadvantage in the Butterworth design. So and his name called to be Chebyshev. Okay. So these two mathematicians gave us some approximation methods so that I can able to design this. Now I already have the Butterworth equation and Chebyshev equation. We will use those direct equations to solve my examples. So here onwards, you should not have some confusion like how sir directly wrote these equations. That's why I for convincing you, I took those equations. Now look at this. I need the equations, ideal equation, that is omega c here. So this is omega, right? As the omega increases, it should get me a sharp at omega c. When omega reaches omega c, I should get the sharp edge. So that's where I write this h of omega magnitude. So because why I take this as magnitude, because like it consisting of h of omega and h of minus omega, right? H of s and its conjugate I call it as h of minus s, right? And when I take its magnitude, this is how we try to take magnitude, right? So this is a plus I, this comprises of a plus ib and a minus ib. Why? Because I told you in the previous time, so every entire signal will be a complex sinusoidal signal, Okay, this is not only sinusoidal. This is not a sine wave. This is complex sinusoidal where my signal will lie in this form. My signal will be in this form. This is what a complex sinusoidal form. Oh, and when I take a magnitude, so I should get like this. So that's where the Butterworth has given a frequency response to design Butterworth filter is 1 divided 1 over 1 plus omega by omega c. You can observe that when omega reaches to omega c, I will going to get a sharp edge. So look at this. If I put omega equal to omega c, I'm going to get half power. What do you mean by half power? When that's what we take a 3 dB in your basic electronics or in analog electronics to reach out the minimum power at half power. So that's where we come 3 dB less and then we plot this, right? So if I convert this to decibels, so that comes to be 3 dB, half power technique. So if you put omega equal to omega c, so this and this get cancels and this is 1 plus 1, that h of omega equal to 1 by 2. So that's how these equations are going to be formed here, right? So this is for pass band, this is for cutoff frequency for stop band, and this is for pass band frequencies. Okay, so this is what we try to give here. Frequency responses monotonically decreases with the frequency response h of omega monotonically decreases. Look at this. So this frequency may not be decrease immediately, but monotonically as you go on increasing the value of c, omega c. If you go on increasing the value of c, omega is constant, and as it increases, omega c increases, this decreases the frequency response. H of omega, magnitude of h of omega decreases the monotonically, right? So this is this is just analyzation and making sure that this equation is approximated to get the output in this fashion. Okay, so this is almost correct. Yes, it has to be correct. That's why it is called as a standard approximation method. Okay, so let me stop here. Let me stop here. In the next class I'll just go to another level. This is just an equation. With this equation we should obtain the roots. When I say that roots are nothing but a poles, so let me discuss once again uh, what is the meaning of characteristic equation. You already know what is the polynomial equations from right from ninth standard. Once again I take those quadratic polynomial equations and then how it is going to be interpreted as poles and zeros in signal science systems. Okay, so this is a start of Butterworth approximation method, and if you are free in the afternoon, I'll complete this one part of derivation today itself. What we'll do, let me wind up. I'll stop the recording now.